Okay, so before we start, that's next week's colloquium by quantum understanding on quantum mechanics and geometry of space-time. But today we are very lucky to have Professor Giufre Vidal from Cognitive Institute, where he's a professor. So he's going to tell us about many new and interesting topics that he's been working on, which go into the general framework of tensor networks. So Giufre did his PhD on working on quantum measures of quantum entanglement. But since then, he's been thinking about ways to simulate quantum systems, but using classical computers. And there's been many pioneering contributions to that area. So not only have these given us better numerical methods, they've also given us a lot of understanding about states of matter, phases of matter, and so on. So it's had a much wider impact than just the numerical community. It's, for example, impacted my own research. People have found new ways of thinking about quantum many-body systems using these tensor network formulations. And it's also sort of shed light on things that we thought we understood very well, things like the renormalization group procedure that's been around for a very long time. But what we tell us today is that these tensor network methods actually shed new light on RG, and yes, that's going to be the topic of this talk today.
Okay, thanks. Nice. Can we play with the lights? Yeah. Oh, yeah, yes. That's good, yeah. Okay, well, thanks, Ashwin. Thank you very much for this nice introduction. And, it's always great to come visit Berkeley. So I want to tell you about this tensor network renormalization, and maybe if I had one slide to summarize the talk, and then we can all go home, it would be this one. And I really need to get used to having one. Yeah, okay, this one. So in this colloquium, I want to remind you of things that you already know. And this is the part, I want to talk about the renormalization group. Then I want to tell you about tensor networks, and that might be a subject that you don't know as much about. So I want to introduce that subject as well. And then I want to tell you how to combine both together, the renormalization group and tensor networks, into a new framework that will hopefully tell us something that we didn't know about the renormalization group. So what's the big question that we're trying to answer? We would like to understand the emergence of collective phenomena in many-body systems. So we have a collection of many microscopic degrees of freedom. We know how they interact. We know they're Hamiltonian, but we would like to understand how they are going to be organized microscopically, collectively. And so this is what now I'll demonstrate what happens nowadays when you have access to a computer. You go online and you can get many pictures. And so one of the things that you can have is these microscopic degrees of freedom. Depending on how they are collectively organized, they can give rise to a metal or an insulator, or maybe a superconductor or a superfluid, or spin liquid, a fractional quantum Hall effect. So you could have a large number of possibilities. I really cut down. I had a super solid there, but they told me that doesn't exist yet, so I removed it. So you can have topological order, quantum criticality. There are many possibilities. And so what's the basic problem we would like to analyze? We are given a local Hamiltonian. This you can think in terms of a lattice system. We're going to work on, say, 1 or 2 or 3 dimensions on the lattice. We have a local Hamiltonian for those degrees of freedom. And what we'd like to do is we would like to understand the ground state of this lattice model. So given a Hamiltonian, can we compute the ground state? And actually, it's not an obsession with the ground state. What we would like to do actually is to understand the low energy collective excitations of the system. Alternatively, we could formulate the problem in terms of this Euclidean path integral or the trace of the imaginary time evolution operator. from which we could also study all these properties. Okay, so the data, the input is a local Hamiltonian, and the output is some object that reflects the collective organization of the degrees of freedom. So to make things extremely concrete, I'm going to be considering or thinking in terms of an example, and this example is going to be nothing but the one-dimensional quantumizing model. Think of this as having a spin chain, a quantum spin chain in one dimension, so a one-dimensional lattice, and we just have that the spins, nearest neighbor spins, have this interaction, and then there is a strong magnetic field on the z direction for each of the spins. So that would be the one-dimensional system, and it will be useful to think of this system as being naturally represented in 2 dimensions. One corresponds to space. This would be the length of the spin chain, and the other one would be the imaginary time, the length of imaginary time. Okay, so we will be interested in some object such as this Euclidean path integral that depends on the coupling constant, and it's natural to think of this as a 2-dimensional object. And we already know the physics. We're not going to learn any physics today. Hope I won't disappoint you with that. We know the phase diagram of the quantumizing model. We just want to make sure we recover the same, that we recover what we expected. So in this case, what we have is that as a function of the magnetic field, if the magnetic field is very strong, then we won't have spontaneous magnetization. There will be some critical lambda, after which we would have spontaneous magnetization. And during this colloquium, I will also equivalently be talking about the 2-dimensional classicizing model. In this case, what we have is a 2-dimensional lattice of classical spins. Each spin could be pointing up or down in 2 dimensions. And then there is this object, the partition function, that very much looks like this Euclidean path integral, and that also naturally lives in 2 dimensions, where now Lx and Ly, they are both space. They correspond to space. And if you look at the phase diagram of this system as a function of the temperature, then it very much looks the same as the one that we had for the quantum system. So this is all well known. It's basic statistical mechanics and quantum spin chains. But I want to use those as an example to illustrate the points I'm trying to make. But more generally, of course, we would like to be able to solve material science, given some microscopic Hamiltonian. We would like to derive properties of materials. We would like to solve quantum chemistry, QCD, and many other things. So we are trying to derive a framework that is valid for all this. And we are not starting from scratch. On the contrary, we are going to take well-established formalism. We're going to take the renormalization group as a starting point. So for the purposes of this colloquium, what do you need to remember about the renormalization group? Well, we're going to look at our Hamiltonian for, say, the Ising model as a particular example of a Hamiltonian in the space of all possible Hamiltonians as characterized by a number of couplings. And for our case, we had maybe a coupling J and a magnetic field lambda. So we could think of that as just being 2 possible couplings, and then after setting the rest of couplings to 0, but that we are really in a space of many possible couplings. And we're going to look at the dependence of these couplings with the observation scale. So we're going to look at our system at different energy scales and see that it naturally describes some flow in the space of possible Hamiltonians, in the space of couplings. And so this is graphically represented in this way, where here we take some section. We are only looking at, say, 2 couplings, K4 and K5. I'm not going to go into the physical meaning of those. I just chose them randomly. But what's important is that as you change the scale, the essence of the renormalization group is the observation that as you change scale of observation, your system can be effectively described in terms of a new Hamiltonian that is related in some way to the previous one, in the sense that as you change the scale, this Hamiltonian is describing some trajectory in the space of possible Hamiltonians. Good, and then this is useful, this picture. Remember that this picture is useful because if you look at the space of possible Hamiltonians and how you have a renormalization group flow in there, you can focus on the fixed points of this renormalization group flow as representative of the phases, the different phases that your system can be in. And in particular, maybe here we have two non-critical phases, gap phases, phase A and phase B, and they will be separated by some surface which contains some critical point. Okay, so this is the standard picture. I'm not saying anything that you don't know, but I'm going to elaborate on this picture. Now, so as I was saying, we can just focus on the fixed points, stable fixed points or critical fixed points, to have to capture the different universality classes of our system. So in this construction, a very important idea is the idea that you can change scale of observation, and one has to be a bit careful with what that means. So let me try to explain or review here what we usually mean by that. What's the change of a scale? What is it that will change the energy scale at which you are looking at your system? And so usually what we mean is a coarse-graining transformation. And Leo Kadanoff and also Kenneth Wilson, they propose concrete ways of doing that. So let's review that. For instance, we could consider a way of changing scale by, in real space, this would be our lattice, a system of spins, by doing this block spin transformation, where we decide that every 3 spins are going to be mapped into an effective spin, okay, before coarse-graining, after coarse-graining. So this spin here corresponds effectively to these 3 spins. Now, a possible way to do that is you look at these 3 spins, you see that there are 2 pointing down, 1 pointing up, and you say, perfect, majority both. If there are more spins pointing down than up, I'm going to replace the 3 spins by 1 that is pointing down. Okay, and you could come up with your favorite rule, and that would define some coarse-graining transformation. Okay, that's in real space. Alternatively, just reviewing quickly what we knew, you could also work in momentum space. And in this case, what you could do is you would regard your partition function or Euclidean path integral as an integral over modes with all possible momenta. And what you could do is you could define an effective, you could break this integral over possible momenta or modes with different momenta into 2 pieces. You could integrate out momenta or modes with momenta between your initial cutoff and the new cutoff lambda prime, from lambda to lambda prime. And if you integrate, so you take your action, right? This is an integral over all possible modes. And what you could do is you could integrate just partially on high momentum, and then this would define some effective exponential, some new Hamiltonian or in more general Lagrangian interaction. So that what you do is you define in terms of the initial one, which is defined in terms of some coupling constants, you would obtain new coupling constants there, and then you would just complete the integral now only on the remaining modes. So that your partition function before and after this partial integration is still given by the same. So this is another way of implementing a change of a scale. You just change your cutoff in momentum space. Okay, you integrate out some of the modes, the large momentum modes. Okay, so we have 2 proposals. There are many more. And so what I would like to talk about is yet another proposal. Okay, so I would like to propose a different way of coarse-graining quantum systems, but within the same framework of the renormalization group. So what I would like is a non-perturbative renormalization group approach. I don't want to have to, at the end, go to perturbation theory to make a calculation, such that my Hamiltonian becomes replaced with a new Hamiltonian and so on, but these are localities strictly preserved there. So I would like a non-perturbative renormalization group approach that is the preserved locality, and I would like it to be universal. Okay, I don't want to go and say, oh, these are spins. Okay, majority rule, majority vote. I don't want to get so close to the physics that then I start talking to the spins and I ask them, how many of you are up and how many of you are down? I just want to have some more universal way of approaching the problem where I don't even need to know this type of species of the microscopic degrees of freedom that I'm dealing with. All right, and and if it's a wish list, then I want to solve QCD. Okay, so this has been this is a long-term project or research direction, and we've been working on it for the last 10 years. And so, how far did we get on this? Well, the good news is, or let me say first that one thing we've done is we've reformulated the renormalization group using tools and concepts from quantum information. That means that we draw diagrams which correspond to quantum circuits. We talk about entanglement, and I'll be repeating these sentences a lot. But the point is not that we reformulated a null problem in our favorite language. I wouldn't be talking to you about this if it was not that this reformulation was led to new insights that were key to making progress. Okay, so it's not about changing notation, though we changed the notation. So the other thing is, in the process of trying to find this non-perturbative approach, renormalization group approach, we came up with some efficient representation of ground state wave functions, something that is known as multi-scale entanglement renormalization ansatz, where you can efficiently represent the ground state of a many-body system, efficiently in the sense that the cost, the computational cost, grows only linearly in the system size, for instance, as opposed to exponentially. So that was an unexpected outcome of this search. But the really good news is that we believe that we have this universal non-perturbative real space renormalization group approach that we can apply on the lattice to arbitrary Hamiltonians. And the key ingredient was the observation that what one needs to do, and I'll repeat this over the next 40 minutes a few times, that the key observation is that if you want to constrain quantum systems, you have to pay a lot of attention to quantum entanglement. And in particular, when you try to change a scale, when you try to go from one lattice to a constrained lattice, you have to realize that there is this property, this quantum entanglement, that you cannot just ignore, that you have to deal especially with. You have to remove it from your system. Otherwise, your system will retain information about microscopic non-universal properties. It's as if you try to flow in the space of Hamiltonians, but your system remembers where it's coming from. Okay, so the key is to identify entanglement as the responsible for this memory that is left in the system, and then attack the problem, remove this entanglement, so that the system, after constraining, does no longer remember where it's coming from. And you can, in practice, just end up with an effective description that does not contain these microscopic non-universal details. Okay, and the bad news is that we haven't solved QCD, so we'll keep trying. So this is not a complete research program, but well, I want to share with you some of the results we have obtained so far. All right, to do that, I need to introduce tensor networks. And I have to say this is a collective effort involving many, many people, and this list does not reflect. We estimate that there are on the order of 200 people working on the research area. So we start this started in condensed matter. We were trying to understand how to efficiently represent frustrated magnets and interacting fermions in 2 dimensions, for instance, or study quantum criticality. But it totally got out of control. And for instance, there was in the last few years, we've seen a classification of gap phases, of SPT phases, symmetry protected topological order in 1 dimension, in 2 dimension, and so on. And the basic formalism that was used for those theoretical developments was tensor networks. So tensor networks started as a formalism to do numerics, and it ended up taken seriously as a tool as a natural way, a natural language to represent many-body wave functions, such that you could have also about phases of matter based on the ability to write them as tensor networks. Okay, so nowadays there are groups. There is the Simons collaboration, for instance, that is pushing towards bringing tensor networks all the way down to material science. So not just as discussion how to solve ideal models, simplified models, lattice models, but whether you can go all the way from, say, a Hamiltonian for electrons and ions all the way to the emergent properties of the system. In quantum chemistry, it's also these are also being used. For classical statistical mechanics, we'll see a little bit of that today. But the focus today will be on the renormalization group. That was what I promised I would be talking about. And we'll also see that recently it's been studied. These tensor networks are playing an increasing role in holography, in the study, in ADS-CFT. Okay, so what's the basic idea? I've been told to be gentle here. But you'll see that I don't know how to write equations. So everything will be in terms of drawings, and it should be fairly simple to follow. So as I said before, we want to represent the ground state of, say, n spins. And we know that we can always do that by taking a basis of each of the spins, of the quantum spins, and then putting amplitudes for each of the possible configurations, up, up, down, up, and so on. And so we are done if we just specify an exponent 2 to the n. See, if this degrees of freedom, if these spins were spin 1/2 degrees of freedom, each one can be up or down, then we would have to specify 2 to the n complex coefficients, and then we would have specified the ground state. And this is a problem. This is a problem because exponentially many coefficients means that we won't get to very large system sizes. Okay, our computer may be able to store maybe the state, the wave function of 30 spins. If you push it, maybe 40, because your computer is better than anyone else's. But you cannot go to 42. Okay, so there is a clear limit to how large your system can be if it takes exponentially many parameters to describe the wave function. All right, so what I'm going to do is I'm going to draw things, and I'm going to explain what that means. But the tensor network will be a way of organizing your exponentially many coefficients. Okay, an efficient way of talking about exponentially many coefficients. And so what I want to do now is spend a minute to explain this equation here. That's as close as it gets when I try to write an equation. I just draw things with an equality in between. And so, so I need to explain what this graphical notation stands for, what this all means. So if you see a circle from today, when you see a circle, you say, hey, that's a complex number. Okay? That's, yes, obviously. And then if you see a circle with one leg sticking out, you have to think of this as an array of complex numbers, actually complex numbers that are indexed by one index. So they are labeled by one index. Okay, this leg represents an index. And so the idea is that when you see a circle with a leg, you think, okay, that's a vector. Okay, a one-dimensional array of complex numbers. So now, you are Berkeley, so if you see a circle with two legs, you start thinking, okay, that can only be a matrix, right? So an array of complex coefficients with two indices. And by iteration, if you have a circle with n legs, you have to think of that as a tensor with n indices. And by tensor, I really just mean an array of complex numbers with a number of indices. Okay, there is no general relativity going on here. Okay, so see, this one here, you already understand this. This circle with n legs represents this 2 to the n complex coefficients. Okay, it's a tensor with n indices. Each index takes two values. So if you look at how many combinations of values you have 2 to the n. So this part here, this is really going. Yeah, I don't know. Okay, maybe I should change the battery here. Sorry. Is it possible I have batteries here?
You continue talking.
Okay, thanks. So what I'm saying is that we understand this part of the equation, and now we need to understand the other one. So here's the second piece of notation, and then we're done. If you see a circle with two indices, we know it's a matrix. This one is also a matrix. If you see that these two circles share one index, then there is an implicit sum over that index, okay? So here, when you see these two circles connected by an index, you have to think, okay, that's a matrix, and there is a sum. So this is the multiplication of two matrices. And therefore, it is consistent with writing that this is another matrix, okay? So that's if you understand this equation, then we're closer to understanding this one. So another example, just to make it a bit redundant, is if you see this drawing here, we have a vector, a matrix, and a vector, right? We have a circle with one index, a circle with two indices, a circle with one index. And so indeed, this would be this expectation value of some observable or whatever. It's a vector matrix vector giving rise to a number, no legs. Okay? Okay, so here's a question for you. What is this? And I've seen cookies left from before, so you can get a cookie or something. What I did hear somebody. A trace of what? Okay, good. So now we are getting close. I mean, we understand what the notation might mean, right? So why do we bother with this notation? Well, imagine they give you this expression here. The first thing you need to know is who is contracted with, what indices are contracted with. And that is the essential information that is captured by the drawing. Okay? It tells you about the different objects that you're trying to contract, which indices are connected with what. Thanks, Ashwin. That's much better. So then we can go back up here, and I can tell you what this is. These are the exponentially many parameters or complex coefficients that we want to represent. And this is a tensor network. It's a collection of small tensors made, say, this one has 3 indices, and you see that most of them have 3 indices only. Excuse me. And so what we say is that we're going to consider exponentially many coefficients that can be actually written in terms of a smaller number. I say this is a smaller number because you could imagine that if this index here takes a number of values that is in, say, this index between 2 tensors takes some number chi of values, say 7, and this number does not depend on the system size, on n, then every time that you increase one particle, every time that you want to consider a system with yet another spin, you just need to add another tensor, okay? So it follows that the number of parameters, if each tensor takes some number of parameters, some constant number of parameters, increasing one spin means putting an extra tensor, then the number of parameters is only linear in the system size, okay? So this is on the right-hand side. On the left-hand side, what we have is these exponentially many coefficients. So that's the basic idea. We're going to just encode exponentially many coefficients in a number of coefficients that's actually only linear in the system size. And of course, that doesn't sound right. What's happening is that we have this huge Hilbert space containing all possible states of our n spins. Its dimension is exponentially large. Excuse me. So we have this exponentially large Hilbert space, and with the tensor network, we are only going to represent some small submanifold there, which depends on many less parameters, right? We want to express objects that depend on exponentially many parameters only using a linear number of parameters. But why should this be interesting? Well, it turns out that we've learned over the last 10 years also that ground states of local Hamiltonians are not generic states in this huge Hilbert space. They are very specific. They behave in a very specific way in terms of entanglement, for instance. There are properties that make them be non-generic in this huge Hilbert space. So our hope is that if this is the space, the submanifold of ground states of local Hamiltonians, our hope is that these tensor networks are actually have some non-trivial overlap with the ground states. Okay, we no longer try to represent arbitrary spin systems as arbitrary states of the n spins. We only care about those that are relevant to physics. And our hope is that these tensor networks are targeting the right subregion. Very well. So what I want to tell you about is a specific example of tensor network, and this goes by the name of multi-scale entanglement renormalization ansatz, or MIRA. And what the first thing I have to tell you about this is that it's a variational ansatz for one-dimensional systems. So what we're trying to do here is represent the ground state of a spin chain, okay, in one dimension, quantum spin chain. But the ansatz itself, the way the tensors are connected, is not as a one-dimensional geometry, but there is an additional direction here, which we will see is related to scale, the length scale. So you see, we use a two-dimensional tensor network to represent wave functions of a one-dimensional system. Okay, so what do we need to learn about this to make progress? The first observation is that in this tensor network, you have variational parameters, which these variational parameters now are inside these tensors, right? So far, I've only told you how to connect the tensors with each other. We have the wiring of the tensor network, but each tensor, these are complex coefficients, and I can choose them however I want. And so I will choose them so that they minimize the expectation value of the Hamiltonian, or we'll find some procedure. I'll describe this a little bit better later, but the important point here is that we have a one-dimensional system, and we're going to encode the wave function with this additional direction, which correspond to different length scales. And this will allow us to use these variational parameters down here to describe properties, local properties of the wave function. And maybe the variational parameters up here will describe more delocalized properties of the wave function and so on. And so this tensor here will keep it to describe, or these variational parameters on the top tensor will correspond to global properties of the wave function. Okay, we have a way of organizing the variational parameters into this additional direction which correspond to length scale. And it turns out that this tensor network is secretly both a quantum circuit and a renormalization group transformation. And so I want to spend another minute telling you in which sense this is a quantum circuit secretly, and also in which sense this is a renormalization group transformation. Once we have those elements, then you'll see why this should be a good variational ansatz for ground states. So let's look into the quantum circuit part of it. So what I'm saying is that these tensors here, actually, you can think of them as being, I'm going to call them disentanglers. You can think of them as being a 2-qubit gate. So for those who don't work in quantum computation, just think of having 2 spins and a unitary transformation on 2 spins. Okay, you take 2 spins and allow for a unitary transformation. If you want a collective change of basis or just a transformation of the 2 spins. So these are the two-body, it's a 2-body gate in terms of a quantum circuit. It takes 2 spins and applies some unitary transformation, and then the 2 spins keep going. And then we'll have these other elements here. So you see there are gates which have 4 legs. These are the disentanglers. And we have also gates that have 3 legs. And this, I'm going to call them isometries. And an isometry is actually, you can think of this isometry as, again, being a 2-qubit gate or a 2-body gate acting on 2 spins, where one of the entries has been fixed to 0. And so that's how you end up with only 3 legs. So from this perspective, if I just rewrite this, replacing every isometry, every 3-leg object with a 4-leg object with a 0, we get this. Okay, and this is the secret quantum circuit that was underlying the mirror. So what is this? How should we think about this? So what this is telling us is that we can think of the variational ansatz that we have as the result of starting with n qubits or n spins in a fixed state 0, 0, 0, no entanglement present in the system. Each spin is in a well-defined state 0. And then applying a quantum circuit that I represent collectively with the letter U. So these are all the wirings and all the gates being applied. And the result of this will be some entangled state, and this will be my ansatz for the ground state of the system. Okay, it's an ansatz that is built by starting with a product state, applying some quantum circuit with some concrete circuitry that is defining here for some reason, and then you apply these gates, and you end up with an entangled state, and that's going to be our ansatz for the ground state of the system. All right, so what you see then is that we start with a product state with no entanglement, and these gates are introducing entanglement into these spins at different times. This is a computational time in the quantum computation if this was a quantum circuit. So what we are doing is that this gate here is introducing some entanglement which corresponds to some length scale. And so as we progress in time, computational time, it's the same as descending to small and small length scales. We're introducing entanglement into this originally unentangled initial state in such a way that the final state that we get, this variation, this meta state, will have entanglement at all length scales, okay, by construction. Okay, so that's one thing that we take with us. And then I also said that this variational ansatz was secretly a Gaussian transformation. So let me explain what that means. And I can go back to what we've seen before, the blocking transformations of Kadanoff, where in this case we will be taking 2 spins into 1. So this is represented as, again, as some sort of quantum circuit, but you have these tensors. These tensors are telling you how to embed 2 spins into, or how to embed the new effective spin into 1, right? So what we have here is the original lattice. We have a number of spins, say n. And then we have an effective lattice with n half spins, half of the spins. And we have a linear map that tells us how to take 2 spins and map them into 1. Okay? And that is the essence of this blocking of spins, added with some original subsequent work by Steve White, how to select this Gaussian transformation. how to choose the variational parameters encoded in here. Okay, so this would be the way we used to think about coarse graining, and now I want to discuss a slightly different way of doing it, which is I'm still trying to map n spins into n half spins. So I still have the original lattice L and L prime are the same as before, but I'm going to use a different coarse graining transformation into a single spin. Okay, I want to block these two spins. But before I do that, by means of this isometry, I'm going to let these two spins interact through a disentangler with the nearest neighbors. Okay? So I want to take these two spins together, but before I do that, I let them have a chat with the nearest neighbors. And that turns out to be very important. So let me tell you in which sense this is important. Excuse me. So let's suppose that our system has short range entanglement. Let's suppose that our system has entanglement between these two spins. If we're going to coarse grain these two spins, it's not a big deal, because two spins that are entangled, if they become one, right? The entanglement is between different spins. If two spins become the same one, the entanglement is gone. Same thing happens down here. So that's good. This coarse graining transformation takes short range entanglement and makes it disappear. But what happens if the entanglement, the short range entanglement, was between two spins which are going to become parts of different effective spins later on? What if this spin is entangled with this one, and this is going to become this, effectively, this is part of this spin and this one there. So what's going to happen is that these correlations, which were short range correlations, are going to be promoted to longer range correlations in the effective description. Okay? There was no mechanism to get rid of this short range entanglement, and what happened is this short range detail, these non-universal microscopic details during the coarse graining transformation have been promoted to longer distance properties, but they are not longer distance. They belong to the original cutoff distance. So the observation then was that this was happening, that short range entanglement was being promoted to longer range entanglement instead of being removed. And so these disentanglers, these additional tensors that we put here, have the mission that they will turn this short range entanglement into a product state. They will disentangle these two spins before the coarse graining transformation. And so the net result is that in this spin blocking, simple spin blocking strategy, some of the method failed to remove some of the short range entanglement, some of the microscopic details. Whereas if we add these disentanglers, then we remove all short range details. So the effective description is free from those. All right, so that's a lot of talking. Let's try to map this back to the renormalization group. And the first observation is that if I give you these ansatz, these variational ansatz, and this happens to be a good approximation to the ground state, actually, this is not just a description for the original ground state, but if I remove one layer, that amounts to coarse graining. You can see that you have also a wave function here for a coarse grained system, right? We went from having n sides to having n half sides. So the wave function, this meta, is not one ansatz, it's many ansatz in one. It describes the system, the ground state, at different length scales. You just have to remove layers and you get effective descriptions at different length scales. And so let me put it back together and then say that what we have is a renormalization group transformation in the space of wave functions, not in the space of Hamiltonians. And that what's happening is that at the given length scale, we have some tensors that define the properties at that length scale, and you can follow these tensors, and that is what defines the flow in the space of tensors, right? You have this flow, which is not the one we wanted, but we still have it. Okay, and in particular, you can study situations where this flows to a fixed point wave function, okay? And that's one of the places where the meta has been most successful. For instance, in quantum critical systems, in 1+1, we've been able to take these ansatz and show that it's a very good ansatz for ground states of systems which are scale invariant. And that works both for homogeneous systems or for systems with boundaries, defects, interfaces. But also in 2+1, we've been able, there are other settings where you have non-trivial wave functions, which are a fixed point of the RG, non-critical ones this time, but a system with topological order. It turns out that you can use this description in 2+1 dimension and obtain an exact way of writing all the the ground state of models known as toric code, quantum doubles, string length models, and so on. Good. So, but people were disappointed because this was not a flow in the space of Hamiltonians, but wave functions. So the good news is that this is also, this automatically, this ansatz also gives you a flow in the space of Hamiltonians. Let me quickly review that. So imagine that you have a local operator on your lattice. So imagine these are your spins, and you have, so each line corresponds to identity on one spin, and you have a term that is acting non-trivially only on 3 spins, okay? So it turns out that you can go and take this layer of tensors and use it not to constrain now a wave function, but to constrain this operator. Of course, you do it in the bra and the cat. And remember, this was a quantum circuit, so this is a unitary transformation. It's a joint, so they simplify, right? It's a unitary and it's a joint conjugate, so it disappears. And when you apply the rules, when you remember that this was a quantum circuit, you end up with an object like this. And what this is telling us is that we started with an operator which is local, acting on 3 spins only, on the original lattice, and you end up with an operator that is acting non-trivially also only on 3 spins. You see, it's acting as identity in the rest of the spins. So what this means is that this Gaussian transformation preserves locality exactly. Okay, you start with a local Hamiltonian, you apply this Gaussian transformation, you get out a local Hamiltonian. So local operators are mapped into local operators, and in particular, you take your local Hamiltonian you started from, you apply this Gaussian, and you get a flow in the space of Hamiltonians. So, okay, so I've been talking a lot. Let me make a quick summary of what I said so far. We have these ansatz, and what I've said is that this ansatz has the property that you can store variational parameters. It has variational parameters corresponding to different length scales. I've also told you that it's secretly a quantum circuit, okay? In the sense that you can complete it to being really a set of quantum gates applied to some originally unentangled set of spins, and that as such, it's introducing entanglement at different length scales. And then I've argued that this ansatz is also defining a renormalization group transformation both in the space of wave functions and in the space of Hamiltonians. In the space of wave functions, the key sentence or the key word was, the slogan was that it removed short-range entanglement, and that was key to defining a proper renormalization group transformation in the sense that we throw away all microscopic details. And in the space of Hamiltonians, it preserves locality. A local Hamiltonian is mapped strictly to a local Hamiltonian. And we could go on, I could talk a lot about this. It's been 10 years, so what do you expect? But the big question is, does it work? Why are we talking about it? Is it a reliable way of describing critical systems? And so for that, I would have to tell you how we use it. And these are technical details, and I'm going to skip those. But basically, you take the Hamiltonian that you want to know the ground state of, you look at this ansatz, you compute the expectation value that you get for this ansatz for that Hamiltonian, that gives you an energy, and then you start tweaking around all these variational parameters so that you lower the energy, okay? And there are very efficient ways of doing that, but that's not the point here. What I want to tell you is what happens after you finish this optimization. Okay, and just with an example, we started talking about the criticalizing model, quantumizing model. So let me show you. In that case, we know that there is a CFT, a conformal field theory, that describes this model at long distances, at criticality. And so this conformal field theory is characterized by a series of scaling of operators, scaling operators that are primary fields with scaling dimensions. There is all this conformal data that tells you how 2-point correlators decay as a power law. It gives you all the information. And so we know the exact solution for this case. There are a number of primary fields, the identity, the spin, the energy density, the disorder operator, fermions, and these are their scaling dimensions. These numbers are telling you the power law that you have in 2-point correlators are arbitrarily long distances. And so this ansatz is capable of capturing those with several digits of accuracy. And so we're talking not about the lattice property, we're talking about the CFT underlying this quantum critical point. And we see that we can accurately describe those. Not only the primary fields, but actually we can also get the descendants. So if you know about CFTs, you would know that the scaling operators are organized into conformal towers. And these conformal towers, at the basis you have a primary field and then some descendants, actually infinitely many. And so what we can see from these ansatz is that we can extract all this information. with many digits of accuracy. Not only this, but a CFT in a conformal field theory, you would also want to know how these operators, these scaling operators, fuse, and this is described by the operator product expansion coefficients, and so they also result with high accuracy from these ansatz. And more generally, you can extract all the conformal data of a CFT in terms of the central charge, the scaling dimensions of primary fields, their conformal spin, and the operator product expansion. Okay, so we start with the lattice Hamiltonian, we apply these ansatz, and we extract all the properties that completely characterize the conformal field theory that describes this quantum critical point. Okay. So the ansatz seems to work. Now, this was our original purpose. We wanted to be able to analyze quantum critical systems, but it turns out that in the meantime, these ansatz became famous for some other reasons. So it's currently under investigation as a realization of the holographic principle. So I thought I would mention that as well. So as I told you, we're trying to describe a system in one dimension, but we use an ansatz that spans an additional dimension corresponding to length scale. And more than this, so it turns out that if you try to characterize how much entropy you have in a region of a given length L, it turns out that it's logarithmic in L in the size of the region. And so the entanglement entropy in these ansatz scales precisely as you would expect in a quantum critical ground state, okay, as a logarithmic. This is some interesting result, which is parallel to things that have been observed in the context of holography by Ryu and Takayanagi. Similarly, from these ansatz, you can argue that the two-point correlator between two operators at a distance L, again, must scale as a power law. And this construction, in order to justify that, you just have to see that in order to connect this point with that point, the 2 points where you are inserting your operators, local operators, to compute the correlator, if you look at the distance within the network, you realize they are log L. So if we look at how many spins we have here, there are L, but there is a shorter path connecting these two spins through the network, which is logarithmic. Okay, and again, this has to do, well, this is telling you that this tensor network is a lattice version of hyperbolic space. Okay, that there are shorter, that the geodesics between two boundary points go through the inside of this geometry. All right, so Swingle in 2009 said, okay, this thing that you are talking about on quantum spin change, blah, 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 this thing is actually a realization, a lattice realization of the ADS CFT correspondence. And of course, in usually the ADS CFT correspondence, we have in mind maybe that we will have a semi-classical gravity theory on ADS, on this extra dimension. These are details that the meta does not cover. The meta is just renormalization group applied to any CFT, not to special CFTs with large N and strong interactions, which is the usual content of the ADS CFT correspondence. But it doesn't matter. This really took off. And now there are many, well, several groups. I'm talking tomorrow. I'm going to Stanford tomorrow, and I realized that half of the people in this list are from Stanford, so I really should, study this subject a bit more. But so they've taken this very seriously. There are several proposals on how to use meta as a lattice realization of ADS CFT. And one of the people, did I forget? No, I have it here. So yes, so Juan is coming here next week. And so I don't know what he means by geometry of a space-time, but he's been drawing these diagrams lately. So, okay. So, great. So let's see. So I'm not doing very well with time. There are another 10 minutes left. I think Ashwin is gone already. Oh, Ashwin, you should leave. You said 5, okay. So the meta seems to work. It was a good ansatz, right? We have the ability now to describe quantum critical systems. So that was work until a few months ago, and then a few months ago we realized that we could do better. And I don't have a lot of time to talk about it, so I'm just going to make an advertisement. This is the person, Glenn Adamley, who is responsible for more of the new results on this tensor network renormalization. which basically allow us to extend this formalism from quantum systems to classical systems. It also allows us to go from ground states to thermal states and to have a much better understanding of what this ansatz is. We no longer regard the meta as a variational ansatz. It's the output of some other process, right? So for 10 years, we were thinking of this as some lucky guess, a lucky guess of how to parameterize ground states. But every time you give me a Hamiltonian, I have to wonder whether this is going to be the right guess for the ground state. You would have to use energy minimization to get there. So now we have found an alternative way of getting to the meta, which is independent of this variational original formulation in terms of variational ansatz. So, and to explain that, I'm just going to go very fast through this, but remember that we started by saying we have this Euclidean path integral for quantum systems, but there is this partition function, the statistical partition function for a two-dimensional classical system, which is very analogous, very similar to that. And so the idea is that for such objects, we do have a tensor network representation. This is not an ansatz for this object. It's an exact or quasi-exact representation. For instance, if you had a two-dimensional classical system, you know of the Boltzmann weights that are giving you the probability of a given configuration of your spins. These Boltzmann weights, typically, if your Hamiltonian is local, can be decomposed as the product of Boltzmann weights for individual pairs of spins. So that automatically gives you this tensor network. Okay, I'm not proving it, but you can believe that the Boltzmann weights already have some local structure, and then you can turn it into a tensor network. So the idea is we have this object already. And one of the things we've been doing, and this object can be characterized in terms of a tensor that is repeated forever. You could imagine that there are periodic boundary conditions here. So that's a torus. All right, so there were, a breakthrough took place in 2006 by Levin and Neif. They taught us how to constrain these tensor networks. They taught us how to apply the renormalization group, a renormalization group transformation in the space of tensor networks. And I don't have a lot of time to discuss this. I'm not going to make justice to this method, which really changed the way we think about constraining transformations. I'm just going to criticize it, okay? Well, I don't think Michael Levin is here, or Neif, so that should be safe. But I'm an admirer of this method. But what I want to point out is that this method has some similar problem to the one that we described for quantum systems, which is that if you initially had some short-range correlations, after constraining, these short-range correlations have been promoted to long-range correlations. So there we are again. You start with a microscopic system. This time could be a two-dimensional classical spin system. You have short-range details that this constraining transformation is not throwing away, is keeping and promoting to longer distances, okay? That's not good. That means that you start with some temperature. You want to flow to, say, in the ISI model, if you are not at the critical temperature, if you are below critical temperature, you want to see a flow to zero temperature. But actually, this method keeps remembering that it's coming from that particular temperature. Okay, so it's not going to flow to a unique fixed point. Depending on each temperature will give you a different fixed point, and that's not good. You would like all the temperatures that are below the critical temperature to flow to the same fixed point. And so what we did was, we did something that looks pretty crazy. That's because Glenn was involved and he knew how to deal with crazy structures. And then you start with your tensor network, you apply these exchanges, and this is not, it's not going to teach you anything, okay? So let's move on. But the important point is that if you repeat the experiment we had before, so if we start with some shortly correlated phase, then because of the new ingredients that we added, we would go from having short-range correlations to no correlations at all. Okay, so the important thing is, again, we introduce some element which happen to be disentanglers, exactly as in the quantum case, in this case of a quantum spin chain. So by introducing these tensors that remove entanglement, or in this case, short-range correlations, you can clean up your system. And so what we have, for instance, is that if we start with a temperature that is right below or below the critical temperature, this is a picture of your tensor. Okay, remember now we have this partition function that is written in terms of products of local tensors. So you get this tensor if you join two indices. This tensor has 4 indices, but if you join them pairwise, you get a matrix. Okay, so now we are looking at the elements in this matrix. This matrix is a 16 times 16 matrix, and initially you give me temperature 0.9 Tc, I look at this tensor, it looks like this. I don't have a choice there. That's the way it looks. But if I cosgrain with this method, then it flows quickly to a fixed point tensor that does not remember where it's coming from. It only remembers that the temperature was below critical. Okay? If we start at the critical point, then these two tensors look very similar because the temperatures initially were similar, but this method is going to cosgrain your tensor into a tensor that keeps looking very similar to itself. If you were slightly above the critical temperature, then it will flow quickly to another fixed point. This fixed point here corresponds to the disorder phase. The original fixed point for temperatures below the critical one correspond to symmetry breaking, so to the order phase. Okay, and you see that these two fixed points are different. And then there is a critical fixed point in between. Okay, so in a sense, we have been able to translate the success from wave functions to classical partition functions. We have a cosgraining transformation that can identify the right structure of fixed points. And the reason why I'm talking about this is because when you apply the same cosgraining transformation to this tensor network, but now we have an open boundary, then as you cosgrain this, it turns out that this process produces a meta automatically. Okay, so we used to think of this as a variational ansatz. Now it's the outcome of some other cosgraining transformation. So the idea is that this object here, this represents the Euclidean time evolution. This is already a representation of the ground state that you wanted. And what we do is we cosgrain this. We are manipulating this ansatz. Sorry, this tensor network representation of the ground state until it becomes a meta. Okay, so this is very different from starting from some variational ansatz. We don't have a variational ansatz here. We have a representation of the ground state, and we just transform it into a meta. Okay, so I think that I'm not doing very well with time, so I'm just gonna skip all this discussion. The same method, when you apply it now to a representation of the thermal state, produces a meta for a thermal state, and that's very interesting from the perspective of holography, because this thermal state is supposed to represent a black hole geometry, a space-like cut of a black hole geometry. And so I guess tomorrow they'll be excited at Stanford. But let me go to a summary. So what we wanted to do was we wanted to reformulate the renormalization group using ideas from and tools from quantum information, and in particular using quantum circuits and the notion of entanglement, paying due attention to entanglement. Our goal then was to have this universal way of proceeding for arbitrary lattice models. In the process, we came up with this efficient representation of ground states, this meta, which is presently receiving quite a lot of attention in the context as a toy model for holography. And we obtained this universal non-perturbative real space RG approach. So it's universal because it applies to arbitrary models. It's non-perturbative. It doesn't depend on perturbation theory. And it's in real space. And so we wanted to have one RG flow in the space of Hamiltonians, but we ended up with 3 flows, one in the space of tensors, one in the space of ground states, and one in the space of Hamiltonians. And the key removal in both, in the 3 cases was, the key ingredient in the 3 cases was the removal of short-range entanglement, okay? Thanks to talking about this in terms of entanglement, thanks to reformulating the renormalization group in terms of quantum circuits and entanglement, we identified what element was key to be removed. And so this works very well for 1+1 dimensional systems, but of course, what we would like to do is to go to higher dimensions, 2+1, 3+1, and maybe eventually being able to say something about QCD. Okay, thanks a lot.
All right, so we have some time for questions.
Are the errors in the scaling dimensions from Mera positive or negative in any systematic way? You showed the exact results and then the results from Mera, and some of them seem to be slightly below and some are slightly above. I'm just wondering have you noticed any patterns in those?
The only pattern we notice is that there are always errors. but that they can be systematically made smaller by using bigger tensors. So there is a way of systematically improving these calculations.
More questions? Yeah.
Is there any hope we can use this method in the future to get the ground state of the interacting electron gas?
In the continuum?
Yeah.
So there is a generalization to the continuum, but it only works so far for free particles, which doesn't make it very interesting. I mean, the guys in holography, they are using it a lot, but to actually solve real problems, we would need to understand how to add interactions in the continuum. That's work in progress.
Okay.
So what's involved in going to 2 + 1 and 3 + 1?
So conceptually, there is no new ingredient that we need to add. We just need to be very patient and write code involving, in 2 + 1, for instance, you have this additional scale direction. So then you are really in 3 dimensions. And the complexity of just keeping track of all the pieces that go into the tensor network is quite large. On top of that, if you want to study systems with a Fermi surface, then there are additional elements. So there is conceptually there is some extra ingredient you have to add. But if you just wanted some critical system in 2 + 1, in principle all the concepts are there, and it's just a matter of working hard towards implementing the scheme.
I've got a question for you. So, in the case of the sort of ground states, right, it made sense that the mirror was a small subset of the actual full possible thing. And that was fine because the ground state is a really small thing. But when you try to actually evolve this for Hamiltonians, right? So, in what sense is the procedure valid? Because it's not like a Hamiltonian is only restricted to a small set of states.
So you would like to simulate time evolution? Is that what?
No. So when you actually did your the RG for Hamiltonians,
Right.
right? So I mean, you were trying to use your ground states that you already had to try to create the expansion.
Yeah, it turns out that the ground state comes in with the Gaussian transformation, and you just have to apply it to the Hamiltonian to obtain an effective Hamiltonian.
I see, and that still captures the full. Because the confusion that I have is to say that for Hamiltonian, I kind of want to understand operators that connect many different states, right? Not just the ground states. So how is that kind of captured there?
So when you apply one layer of Gauss-Graining, you're going from n sides to n half sides.
Yeah.
So you're actually throwing away a lot, but you're keeping a lot as well.
Right, sure.
So what you're doing is you are just looking at your Hamiltonian and somehow managing to refocus your attention to the low energy sector of that Hamiltonian. But this low energy sector is huge still.
Right, okay. Right. Okay, good. I think we don't have any more questions, so let's thank the speaker again.
Fantastic.